Hello, we are from ChemPraxis, and in today's video, we will be covering Physics Paper 3, Variant 3, February-March 2025, Question 1. In this experiment, we will be investigating an electrical circuit. As you can see with the diagram right here, we have a resistance wire taped onto a meter ruler with a long connecting lead connected in between the resistance wire, which we will need to vary in length x later on to change the resistance. So these are the apparatus that are provided for us for the setup. As you can see, we have the wires with crocodile clips, multimeter, switch, resistor, 1.5 volts of power supply, and the resistance wire attached to a meter ruler. Keep in mind that some of the apparatus like the multimeter and the power supply may vary with different schools. Okay, now let's assemble the apparatus according to the diagram. Okay, so now that we have set up the apparatus, let's proceed on. Now, following the instructions, we will need to use the long connecting lead and clip the crocodile clips on the resistance wire so that they are approximately 0.45 meters apart. The reason that they say that it is an approximate is because that the crocodile clips on the connecting leads are not narrow enough for us to place the crocodile clips accurately on the mark where we want it to be, so an estimation is sufficient. So after connecting the connecting leads, we will need to close S and record I, which is the current. Okay, let's move on to the demonstration. So now we will use the clips to attach onto the resistance wire. You can place the clips anywhere in between the meter ruler as long as it gets a length of approximately 0.45 meters, which is 45 cm. Make sure to attach the resistance wire in between the teeth of the crocodile clips and not at the very tip or the very back of the crocodile clip to ensure a firm connection between the wires and the connecting leads. Then we will close the switch as we can see here, we will get a reading in our ammeter which is 37 milliampere. So back to our question, we can now record the X, which is approximately 45.0 cm. Now, as we can see here, the question has set for us the unit that we are going to be using, which is in meters. So we will need to convert our value from cm to meter. Now, why did I use 3 decimal place? It's because that as I'm using a meter ruler, the smallest unit that I can measure is 0.1 cm, which converts to 0.001 meter. In exams, we always record the value to the smallest unit that our measuring equipment can measure, which in this case, we will need to write 0.400 meter. Same goes to the current. As we are measuring the current in milliamperes, and the smallest unit that the ammeter can record is to 1 decimal place, we will need to record the current as 37.0 milliampere, and as the unit is also given for us, which is ampere, hence we will need to convert and we will get 0.0370. Now moving on, we will need to choose another 6 sets of length x and record the corresponding current I that will give. So first of all, we will need to set the maximum and minimum values of x that we will be using, and we must use the maximum range of the apparatus. Now, how do we determine the maximum and minimum values of x to use for the experiments? Now, always remember for every circuit experiment with resistance wire, it is always the same. For the maximum length, we will need to cover the entire meter ruler. But keep in mind that we have tapes wrapped at both ends of the meter ruler, and we will not be able to attach the conducting leads to the end of the meter ruler. So we can only vary our lengths in between the tapes. For the maximum length of x, you will typically need to use 80 cm or above, which in this case, I would use 80 cm. For the minimum value of x, you will need typically to use 20 cm or below. For this experiment, I'll be using 10 cm. So now that we have our maximum and minimum values of x, we can set the remaining values in between the range as long as they have a regular interval. And right here, I have completed the experiments, and let's talk about the number of significant figures of your readings. Remember, for any calculated values from raw measurements, always follow the smallest number of significant figure of your raw value, or 1 significant figure higher than your raw value with the smallest significant figure. So for our current, as we are using 3 significant figures, hence our 1 over I can be 3 or 4 significant figures. Moving on, now we will need to plot a graph of 1 over I on the x-axis against x on the x-axis to find the gradient and the y-intercept. So this is my graph. As you can see, all the points are as close as possible to my line of best fit, and at least 50% of my grid is being used. Always make sure to label every 2 cm, which is one big box, on your scaling, and the intervals of the scaling are regular. For example, you can use +1, +2, +5, or +10, so on and so forth, as long as it is easy to calculate with your scale. And always remember, for physics graphs, you will not need to start from 0. Adjust your scaling and starting point so that you use 50% or more of your graph. Now we will need to proceed on to find gradient and the y-intercept. We would use the rise over run method, which is drawing a triangle between the 2 coordinates picked. Always pick the point that your line of best fit passes perfectly through, and always try to use the widest range of coordinates in your line of best fit. Now that we have our coordinates, let's proceed in the calculations. So for the gradient, we can just use y2 minus y1 over x2 minus x1 method to find, and for the y-intercept, since our graph is not starting from the origin, we will need to use y equals to mx plus c method, as we could not see the y-intercept directly. For the calculated values, you can do 3 or more significant figures. In this case, we have the gradient as negative 13.97 meter to the power of negative 1, a to the power of negative 1, and y-intercept as 34.0, a to the power of negative 1. Although it is not a requirement for you to write the units here, but please write them down as a habit, as we will also need to use the units for the questions later. Moving on to question D. It is suggested that the quantities of I and x are related by this equation, where a and b are constants. Using our answer in C3, determine values of a and b. So if we look at this equation, it will overlap with the equation of y equals to mx plus c, where our a is our gradient and b will be our y-intercept. So now we just need to mention that a equals to gradient and b equals to y-intercept, then we can write the final answer. Remember to include your units, which is the same as the units that you have written in the previous question. Now for question E, theory suggests that a equals to negative p over q, where p is the resistance per unit length of the resistance wire and q is 1.5 volts. We will need to use our values of a, which is our gradient, to calculate the value of p. So we will need to rearrange the equation to p equals to negative a times q, and just substitute in the values, and we will get 20.955 ohm meters to the power of negative 1. So how do we get that unit? As you can see from our units, from a and q, we can use the equation v equals to IR to find out that v over I would get us the ohm unit. So this is the end of the question. If you liked the video, don't forget to like, share, and hit that subscribe button for us. This is ChemPraxis, and thanks for watching.